Okay, yeah, sorry about that. Let's start. Do you have any questions? Okay, so let's finish American option today. And so we're almost there, right? What did we say, right? So we are discussing basically, right, the analytic solution, right, for perpetual put. All right. So let's remind ourselves, right, of what the important details are for these things. So first of all, one thing you should notice, right, is that, so in general, right, we have a function Vt St, which is equal to Vt for American option, all right? Any kind of option, any kind of American option, right? I guess with exploration, right? Some finite exploration. Now, one thing is when, when we somehow have very long, right, exploration. So you could do this as an approximation, right, too. Then, what we say here is approximately true because, right, I guess there's no real perpetual option out there. But when this is true, right, and notice that we also, it's very important that because, right, the Black-Scholes model is time homogeneous, right? I think Eugene, right, talks about interview question about assumptions of Black-Scholes, right, on her interview, and exactly, the most notorious, right, assumption on Black-Scholes is that, they wouldn't use the word time homogeneous, right? They would say that the volatility is constant, but it's basically the same thing. In other words, so like this, right? So basically the dynamics that change to the stock price, right, only depends on the stock price itself, right? The interest rate is assumed to be constant. The volatility is assumed to be constant. Actually, right, the reason why we say R is constant here is because we do not go to the interest rate model chapter, right? We don't have time for that. But basically, you could extend this to something like this. So you could include a time-changing interest rate model where this guy also is a stochastic process by itself. This is possible, right? Under this, I think, modification, you still have, right? You still have this, I guess, being called a Black-Scholes model. But, this is not what I have in mind when I say Black-Scholes. This is what I have in mind when I say Black-Scholes, right? But I think people can still recognize this as Black-Scholes. The most important thing is, again, right, here sigma is still a constant, all right? Now, when sigma, right, is improved like this, so you could keep R constant, but you change sigma to be like this. Then now, right, and when you do this, you are implying that this is a stochastic process. Then this is no longer a Black-Scholes model, right? And the most, I guess, important or the most popular, right, extension in this direction is the Heston model, right? So you should look at Heston model. I'm not sure if you see that in computational finance, but basically, I think there is a dynamics for sigma t. I'll just write out something like this. It's been a while since I reviewed it. Something like this, I believe. And then the most important thing is like this. Yeah. So check me on that. I'm not so sure, but Oh, I think there's time reversal here too. So there's something about this. So anyway, right? Maybe something like this. So it's time reversal. So could be something like this even. So basically, this model says that the volatility, right, centers around some level, sigma, right, and it will always revert back to this level with some rate k. Anyway, right, very interesting stuff. Again, unfortunately, we don't have time to go into it. Point is though, right, that the assumption, right, of Black-Scholes, if anyone asks you about that, is about this guy being constant, right, which is obviously not true. But then again, right, you can definitely defend it or saying that, it's still reasonable to use as long as you have a short time interval, like, I don't know, 1 month, right? In 1 month, the volatility is not going to change that much, hopefully. And so the Black-Scholes is still a good approximation, that kind of thing. Anyway, right, going back to what we want to say here is that when time is infinity, under this very particular model we're looking at, right, then it basically means that where we are evaluating our option price is immaterial, right? Because you could look at this today, and you can look at this 1,000 years from now, right? Which is weird, but the dynamics of the stock won't change. Okay. So in other words, right, where you are looking at for the option won't matter because time is infinite, right? There's no horizon waiting for you, right? So another thing you can also pay attention to is, right, option price, right, usually, right, depends on t via t minus t. All right. So the duration, the time to expiration, it doesn't depend on this directly. And when this is infinite, right, that factor disappears. All right. So all these I'll leave it for you to contemplate further. But basically, in this situation, right, we have just this, right? So no longer, right? No longer having the t dependence. And this makes everything very easy, right? At least in theory. And so let's recall, right, our equation, right, for American option. So the equation, right, comes in two parts. The first part is that, very usual, right? And I'll write with t here just in case, right? This is the part the Black-Scholes PD part, right? So this part should be 0 in general, but for American option should be negative because it's super martingale, non-positive. And then, right, we remember that it will be 0, right, if you stay above the payoff, right? And the last condition is the value must be above the payoff anyway, right? So 3 conditions, right? 1, 2, and 3. Together, right, capture the PD, right, if you will, for any American option with payoff function phi. Now, when we drop the dependence on little t, right, because now time is infinite, expiration is infinite, then, well, basically we drop this guy, right, and then this guy. So what we have now is minus RV, right, plus v sub x Rx plus 1/2 v sub xx sigma square x square, not negative, then is equal to 0 if you are above, and you must stay above anyway, right? Sorry. And so this, right, actually, so by the way, right, let me say something about this first, right? The ODE, right, minus RV plus v sub x Rx plus 1/2 v sub xx sigma square x square equal to 0, right, is called an Euler equation, right? Not that the name really matters, but it's just good to know. And it has an analytical solution. So this is probably one of the places where, when you apply to this program, analytical solution, you have to have ODE, right, prerequisite. And I don't know, this is one of the places where you use it, right? And I think in your homework, you already look at the solution anyway. Yes, but it's good to kind of go back to and take a look at this. So how do you solve this analytically? How do you find a formula for it, right? And so I encourage you to think about this a little bit. But back in the day when you study ODE, and if you, right, the analytical solution actually is a little bit forced, but it's kind of nice in a way. But a lot of times when we mention this for this kind of thing, it's mostly through a guess. Basically, you observe the structure of the equation, and you see that certain kind of functions make sense as a possible solution. And that's it, right? And you plug in and you try to solve for that specifically. For example, here, right, what can we say, right, that the solution must look like? Well, you observe, right, the structure of the equation actually is very particular. You have the original function itself times a constant. You differentiate once, and you times x. You differentiate twice, and you times x squared, right? Now, why does that matter? What matters is because, right, at the end of the day, all these have to add up to 0. So if they add up to 0, what that means is they must be the same kind of function. You know what I mean? For example, right, to demonstrate what's not the same kind of function. Well, very easy. Suppose you try sine, all right? If you try sine here, then you differentiate one is flip to cosine. You differentiate one more time, you flip to minus sine. Right? Obviously, sine and then cosine times x and minus sine times x squared are not the same creature, right? So they cannot cancel each other out to be equal to 0. Okay. So in other words, right, whatever function that v could be, right, not that there must be a solution, but if there is such a thing, then v must be such that v and vx times x and vxx times x squared must be of the same type, right? Well, of course, right, the only thing that can be different is maybe, the constant in front of them, right, that allows them to add and cancel. But, this must be the same, right? So it's a long-winded way to say what? It's a long-winded way to say that this must be a polynomial. Or really just a power, right, of a x, right? Because clearly when you differentiate, right, you bring the constant down, but you subtract 1, so when you multiply by x, right, it stays in the same structure, same type, okay? And then it can cancel. Does that make sense? So that's the only trick to this kind of part, okay? And so, right, so what I'm trying to say is you can always solve this, right? You plug in. So basically, this is called a guess, right? Or in some fancy circle, they call it an ansatz for some whatever reason. I don't know. This is a fancy word that I, have no idea. Probably some sort of Greek word or something. Who knows? Anyway, right? You plug in. And basically, right, you can see that the x to a p cancel out, right? And then all you have left is the equation for p, which is minus rp, right? Plus p times r, I believe, right? Plus, wait, am I right? And then plus 1/2, right? P times p minus 1 times sigma squared is equal to 0. That seems weird, right? Did I do something wrong? Oh, no, this minus r, not minus r times t, minus r. Okay. So here, right, then, any question about this? so, right, you can clearly, right, this is a quadratic, but, just eyeballing it, see that p equals to 1, right, is a solution because this is 0, that's 0. So p equals to 1, and then p equals to something else, right, is a solution. What is it? I don't remember this part. Let me see here. Minus 2r over sigma square. Okay. Basically, right, I mean, you just use a quadratic formula if you want. Okay. So what does that imply, right, about the solution of the ODE? Well, right, so now again, right, that's theory of ODE, but it's pretty simple. What that means is you have two choices, right, x or x to this power, right, as possible solutions. Now, right, then you have a little bit of linear algebra, right, or linear ODE coming in, which says that then any linear combination, right, of solution of this type will still be solution because this equation is linear, right? This equation is linear, right? So what, yeah, right. So what happens is, right, so the ODE is linear, right? So any linear combination so maybe I shouldn't call it V of X, right? I don't know. What should I call it? Right, all possible solutions to the Euler equation. Okay. So R because you can choose any AB you want, right? So notice that this discussion here, right, has nothing to do with what phi looks like, right? It could be put, it can be called, whatever, right? This is nothing to do with the original equation, because the original equation, right, that we're looking at is actually a obstacle, right? ODE like this, right? Which has only the Euler as one of the part, right? So the min of this and phi of x minus phi of x, right, is equal to 0. Yes. So this is the fancy way, right, to write the above. But basically, you see, right, either this is 0 or that is 0, and the other one of them must be, both of them has to be non-negative, right? That's what I say. But right, so this is just discussing when this is 0, right, and this is a possible solution. But of course, right, it doesn't tell us what A and B are. Okay. So again, right, do remember and appreciate the difficulty of this kind of thing, this kind of equation, right? So what the difficulty is like this, right? Basically, you try to, let's say here's x, all right? Suppose you have a phi, right? Let's say it looks like this, who knows? Okay. So that's given, right? You can plot it. And then, right, well, you know that, right? There are some parts where, let's say maybe here, that the solution is the ODE itself, right? So this is the ODE itself. Right, which is this guy, right? And then if it's not the ODE, then it must be phi, right? Because it's greater than or equal to, right, phi, and is either, right, equal to phi when this is equal to 0 or that is equal to 0, right? So I think this is the advantage of this structure, right? It tells you that either this is 0 or that is 0, right? So when the ODE is above the payoff function, right, then you follow the ODE. When the ODE is, I guess, below the payoff function, then you follow the payoff function, right? So again, right, all good and stuff, except, right, the key is we do not know where these are, right? So basically, right, the biggest challenge when you solve an obstacle problem is you don't know where, right? So let's call this region, right? The collection of X, what this is true is the continuation, right? And where the opposite happens is the exercise, right? The biggest challenge is, right? Notice there are region of X, all right? Region of X values. We do not know where they are, right? No idea about the structure, their structure in general, right? So obviously, here's something you do know, but it doesn't really help. You do know that they must be intervals, right? Again, you notice there's some real analysis going on here. There must be intervals because, it's like, well, should they be interval? I think they should, because these guys are continuous, that kind of thing. So they cannot be too bad. On the other hand, right, they could be more than one intervals, right? You like what I was doing here, right? There could be more than one intervals. You don't even know how many intervals there could be, right? So that's the bad news, right? Because the more intervals they are, right, the more complex you have to do your analysis. And in fact, you don't even know, right? So here, right, you want to use the phi, right? You want to use a payoff function to give you some idea about what this region look like, all right? And if you could, and if you have a very good idea on how this region looks like, then you're almost done, because that's really it, right? Because, so the idea is this, right? If we do know what these guys look like, then all you have to do is, right, you do a generic ODE on the continuation region, and the exercise region would be the payoff function. And then in between, right, notice that you are solving an ODE, right? I mean, at the heart of it, this is ODE. So whatever you're solving must be rather smooth. In other words, right, they must match in terms of the value, right? And you can match even the derivative, right? And higher derivatives, for example. So this is like the spline idea, right, in numerical analysis. I'm not sure if you looked at spline. You might have, right, in numerical analysis 1. But that's exactly like a spline idea, right? You have one piece of function, another piece of function. You know that the way they connect must be rather smooth. And that allows you to decide the coefficients of the ODE as well as where, right? Because this is also a parameter in this part that can be used, right, to solve. Does that make sense? So, right, the biggest challenge is exactly deciding what this guy looks like. And that cannot be done in the abstract unless you know more about phi. Okay, so far the argument is independent phi, but now we will utilize phi. Okay, so now, right, specializing, right, you know where we're going. We have this, and this allows us to. So I'm not so sure, right? The argument we are doing is purely financial, but I think you can also do some mathematical argument, I believe, right? Which leads to the same thing. So the financial intuition, right, is that because, right, this is a payoff function, you have reason to believe that, right, when time is perpetual, right, when exploration is perpetual, you will continue, right, as long as the stock is above some level, right? And you will exercise as long as the stock is below that level. Again, right? Purely a guess. And the guess is reasonable based on, financial intuition, or you could do mathematical intuition. But this, right, notice this greatly simplifies the structure, right, of the region, because this is K, right? And we argued before, right, that this guess L star must be here and, right, here is where, right, you continue. So here's where you follow the ODE, right? So to the right, you follow the ODE. So that would be something like this. And to the left, right, you follow the payoff function. So it must be like this, right? So this looks like your V, right? Again, purely as a guess. Notice also, right, we draw this picture, right, suggesting that the payoff, also the value of the option goes to 0, right? Is this correct intuitively, or we're just drawing something, right? Would it pick up like this? You know, that kind of thing. How do we know? Again, right, all these things, the more intuition you have, the better you can get a hold on your solution. So what do we know? Well, you see, why is V a decreasing function? That's where I think I know where you're coming from. Are you using a super martingale? Nope, that's wrong. That's very wrong. Okay, and that's very easy to confuse here, right? Exactly, that's a good mistake, but it's a very wrong mistake. It is, well, of course, this is a mistake. The reason is this, right? When we say VT is a super martingale, all right, sorry, well, discount it, right? Doesn't matter. What really means is the expectation, right? So first of all, it's on average, it doesn't really matter, is decreasing. But notice in T, all right? The graph we're drawing here is in X, okay? This happens a lot in this kind of analysis. We make some statement in time, and then we switch back to, you know, analysis of value depending on the stock price, all right? And the two statements are not definitely have nothing related, all right? Because obviously as time increases, doesn't mean the stock price has to increase, yes? So yeah, right? So that's very easy to confuse. That's perfectly fine. So here, right, this is X stock price. So the answer is simple, okay? It is important. You will see how it's used. This is correct. The reason, though, is not because of, you know, this property, right? It has nothing to do with that here. It has to do with the option we're looking at, right? The payoff function. Because obviously, right, as X goes to infinity, K minus X plus goes to
0.
Correct. So obviously, the value of the function is the value of the solution itself also goes to 0. All right. That's so again, notice a lot of things now comes from the payoff function structure, right? Nothing to do with, right? The equation itself uses the martingale structure. That's it. Right now we are studying the equation, how it moves, and that more or less kind of got played by the feet. Right. So okay. So any questions so far? So what we're having, right, is that this guy is a x to the minus 2r over sigma square, right? Something like that, yeah. Plus bx, right? And this part right here, right, obviously is just k minus x, right? Because it's, you know, the positive part, right? So there you go, right? We almost know what our v function looks like, right? So both of these equals to v, right? So to recap, you know something like this. So x. All right. So you're almost done, right? Except what do you know? K is given, right? So what we need to know is we need to solve, right? For A, B, and L star, right? Then we're done. I mean, not done yet. There's still technically the last part where after you do this, then you need to check that whatever you're proposing here fits, right? This structure, right? Or this structure. Well, that's easy, right? Because actually, even at this stage, you see that, yeah, it does, right? I mean, it's above, right? And then when it's above, it's 0, etc. Right? But technically speaking, after you solve this, you still need to check back. But I don't think there's any difficulty there. So solve for this is the biggest challenge. Okay, right? So how do we solve for this? Well, in math, right? Anytime you want to solve for something, you need an equation, right? What else? So where do we get our equations? Well, right, again, notice how, right, we draw this picture, right? We didn't draw it like this guy jump above here and then go down here, right? Suggesting that, right, so V is a piecewise defined function, that's very clear. But V, right, should be smooth where things got mashed, right? So suggesting that V is continuous, right? And differentiable at L star, right? So meaning something like this, right? K minus L star is equal to A L star, right? To the minus 2R over sigma squared plus B L star, right? So that's the first equation, that's continuity. And then differentiability says minus 1, right, is equal to minus 2R over sigma squared A L star minus 2R over sigma squared minus 1 plus B, right? This is differentiability. It's not really differentiability, right? Continuously differentiable. It's really just differentiability too. Differentiability at L star. Because, if you have the left derivative not equal to the right derivative, then it's not differentiable. Okay. Any questions so far? So now, right, here comes some rather interesting difficulty, technical difficulty I want to pay attention to. Oh, by the way, right, I also strongly encourage you to try to see the intuition for this, right? Again, it's very natural and it seems like the right thing to do, but you want to step back and see why does it seem right? It's right because it's aesthetically pleasing, which is irrelevant, right? Or because there's some intuition, right? So obviously, right, continuity here seems good because, right, we're looking at the option price, yes, as it's above the continuation, as it in approaching the exercise region or approaching the continuation region, right? Notice, right, again, it's not moving in time, all right? So that don't get the intuition in the wrong place. But anyway, right, one would not expect that as price moves across L star, somehow option price jump, right? Option value jump. Of course, also notice that there's something a little bit vague about that argument. Technically speaking, below L star is not really a price, right? Because there's no trading, right? Because anyone who has the option around here will start exercising immediately, right? So price or whatever only makes sense above here. Nevertheless, right, we can talk about value of the option. And yes, right, it makes sense that value of the option doesn't jump, right, across this. What's more, right, seems like we also say that the delta, right, doesn't jump across. Now that one is a little bit harder to digest because, again, what does delta mean, right, when you are not even trading? Anyway, right, but it seems okay. Now, one thing that you will see though, right, and that's where we'll go next. Also, I want to say that, right, even from the mathematical point of view, it's not too hard to digest that this must match smoothly because, we're writing down, right, node E, and you are doing something like derivative, right? So by the way, right, this could be prime and double prime, right, for all we care, because we're not in the, PDE section, right? And so we're writing down, right, derivative and such. And if you want to write this down in second derivative, you better, right, be smooth. Otherwise, what are you talking about when you differentiate? Yes. So anyway, right, this is reasonable. But again, right, try to contemplate why. Now, don't just do it because it looks good. But then, right, notice how many unknowns do we have? We have 3 unknowns. So far, right, we've only do 2 equations. Yes. So where do you think the last equation comes from? We need one more, right? Because we have 3 variables. Where should the last come from? No one is suggesting matching the second derivative?
I would suggest that, but Professor Larson yesterday said that that's wrong.
Wow, he spoils my surprise. Great, you guys are learning this in his class too. That's wonderful. Why is it wrong?
I think I didn't review the notes, but I think it worked. It just works out somehow. I'm not too sure.
Oh, it's good. It's good. You know, first you should remember what your professors say. You know, I think that's always good, right? But second, remembering what they say, and then understanding why they say so, right? It's important. Okay, so right, you shouldn't, right? But why not? And again, right, I would like to tell you that you should really contemplate these kind of things on the math side. Again, I know it's technical, but it's good to think. And one thing, right, is that it's very natural to do so. And to see why it's wrong, just go ahead and do it. Okay, just go ahead and do it. And see for yourself, right, what happens. So if I continue at the second derivative level, what equation do I get? I'll get 0, right? Is equal to, well, whatever, right? Some constant times a, and that's it. Agree? Do you agree? That means what? A is equal to 0. Yes, that's the conclusion I would get if I push the second derivative. All right. Now, what does that mean in terms of the picture? And now, right, you look back at the picture to find out what's going on. It's perfectly clear, right? The second derivative is about what? Second derivative is about convexity, right? So you're trying to match the slope of the tangent line, the value function, that's fine. Now you're trying to match convexity. Well, obviously on this side is a line. So convexity is equal to 0. That's what it's telling you. Now, if you want to match convexity on this side, then what it says is you must be also a line on this side. Correct? And obviously, the only line that can be on this side and match slope and derivative is, and the value is the line itself. But that's a contradiction, isn't it? Right? Because obviously we say that from L star forward, you must be above. So understand now?
Yes, thank you.
Oh, it's fine. I'm not critiquing you, Kareem. It's very good that you memorized that. I'm just saying, right? The argument is very subtle, right? So I highly encourage that you think about this kind of thing, right? Okay. So yes, right? So the second derivative doesn't do it for us, and I want you to understand why. But also, right, that brings back to the question of what motivation do we have to match these things? Again, right, finance is okay. But I find the finance not super rigorous because what we just said is matching the value of the option as it goes across. That's perfectly natural. Everyone would agree. Matching delta, that's a little bit weird. But obviously, the gamma doesn't get matched at all. So that questions the finance, I mean, so we're not really exactly doing finance here, by matching, but it's really the math that guides it. Okay, again, it's really that we are writing these things down. So there must be some level of smoothness, but you cannot push it too far. That's the message here. But anyway, so what's the third equation? So the third equation, is subtle. It's not really obvious. It comes from something else. And actually it comes from this picture, You, again, this is actually when people do math, me included. Sometimes we just write down symbols and we are not even thinking what the symbol is telling us. But the more you think, the more helpful it is. Notice, this guy, what sign is this power? This is negative, So it's a decreasing function. This, we don't know what B could be, but whether it's positive or negative, it will keep going to infinity or will keep going to negative infinity, whatever B is. But whatever B is, if B is non-zero, what that means is when X goes to infinity, if this truly is our solution, then we will either shoot up or shoot down, because this guy will go to zero, which contradicts, totally, what it cannot go below zero because it's an option value. It cannot shoot up because, of this. So what that means is B is understand? So, all, I want to explain all this to show you that the thinking, can be a little bit subtle, It's not just mechanically pushing, symbols, that kind of thing. You have to really contemplate, what's going on. All right, any questions about this? Okay, so all in all, now you can solve for this, knowing that B is equal to zero, you can solve. And let us skip all the surprise, And the only thing I want to discuss is L star now, A and B, A, you can look up in the notes, but L star is 2R over 2R plus sigma squared times K. Okay. So first, before we discuss this, let's go back. Well, so now, after all this discussion, let me ask this. Is V double prime, the word is does, exists at L star? So after we solve all this, after you see what we've done, blah, 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 we have got everything. Now you have to go back and look at your solution because, this is part of checking to make sure that it fits, the bill, Does this happen?
I don't think so.
The answer is no, Because clearly this has a convexity, It's positive convexity here is equal to zero here. So clearly it's not twice differentiable. Is V prime does exist, at L star because of this, Is in fact equal to -1. So, that calls to maybe cause some problems, Because I guess in your training from, ODE, whatever. Anytime you write something like this down, you better make sure it exists, right? So what's going on then? What are we saying here? Is this still a legit solution, or are we making a mistake that this is not even a solution?
I think it's okay because the probability of being at L star is 0.
Very good. Yep, that's where I'm going next, right? That's very good. So first of all, right, one thing I want to say is, again, I'm not sure. I think you guys don't get exposed to this, but the more complex the equation becomes, the less regular you expect the solution to be. And then, if you take more math, they have all these ideas of weak solutions, that kind of thing, right? So the ones we encounter here is not super weak, but it's not classical in the sense that the second derivative here, right, has some hiccup at some point, right? But overall, right, the structure is still valid, meaning, right, you stay outside that point, anywhere else, things are fine. Okay, so that's maybe one thing you can say. The second thing has to do with what Kareem was saying, that ultimately, right, you have to kind of check where this equation comes from. And it comes from, right, ultimately I guess I didn't write down, the super martingale property. Yes. So as long as the super martingale property holds for this kind of V that I plug in, then I'm okay, right? Because that's actually what I'm after, right? So here you have to think of what you are trying to express, what you're trying to describe, all right? And the answer is yes, the super martingale property still holds for this V that I'm writing down. Why? Because, right, what we're hiccuping about, if anything, is the second derivative, right? This term right here. All right. And it happens, right, when the stock price is equal to L star. All right. Now, how often does the stock price equal to L star in real life? How often is it? How many times, right? And this is what Kareem was saying, that the stock price is equal to L star with probability 0, the amount of time, right? And again, this can be gets a precise expression in terms of local time, that kind of thing. Very, very advanced topic, right? But what I want to tell you is that, right, things are okay, right? If you think in the big picture that, one point won't spoil the property of the math, right? But do pay attention that we are in some rather, right, more advanced situation where, right, classically, we don't expect things to hold everywhere. But, some trouble point as long as it's not too severe in terms of the frequency that it happens, then it's fine, right? Okay. Any question on this? All right, so now let us focus on this, right? Because again, this may look just like a symbol, right? But it has a lot of meaning if you try to see what it's trying to tell you, right? So it's not just, right, a symbol, but when you solve this, right? Because remember, right, this has financial implication, right? We say that if below L star, we exercise, above L star, we continue. So we can try to, right? So this is called a reality check, all right? Once you have the answer, you can try to plug in different parameters to see how, right, this solution change, and see if it agrees with your intuition on how reality should be. Because if something doesn't match, then that means that either your intuition is wrong or reality or the solution is wrong, right? So it's one good way to check, right, that at least your solution looks okay. All right. So what do we mean, right? For example, if K increases, right, then what? L star here increases, right? I mean, just based from the formula. Does that make sense in terms of the intuition? That if the strike price, right, rise, then the amount of time you can wait, right, until you exercise has to also rise. Does that make sense or not? Right, because the payoff is ultimately L star, right? K minus L star in some way. So in quote, right? So what this suggests actually is you shouldn't be greedy, right? You would think that if K goes up, L star would go down or something. But you are very greedy, right? Because you are only trying to get a payment. So if K star goes up, then you can afford to wait less, right? Because remember, right? The longer, the smaller the L star, the more you have to wait, right? For that to happen. So if LK goes up, you can afford to wait less because, right? This is the amount you get paid. So you get paid the same, right? By waiting less. Okay. Now that brings the question, right? What makes you wait less or more, right? What makes you wait longer or shorter? That's what I mean, right? And so that brings us to this other one, right? If R goes up, does L star goes up or down?
Down. Down.
You say down, right? Why? I mean, mathematically, why?
No, because the denominator would increase.
Yeah, but the numerator also would. In fact, right, let us think financially. If the interest rate goes up, should you wait more or should you wait less for your time to exercise?
Should wait less.
Right, because the more you wait, the more you get punished, right? Of course, the more you wait, there's a balance here, right? But the more you wait, right, the less, right, it will be meaningful now, right, in terms of present value of time because you get discounted more, right? So this seems questionable. And the way we answer it, right, is here's a very simple trick. Right? And so, of course, when R increase, sigma square over R decrease. And so 2 over 2 plus sigma square over R increase. Agree? So L star increases. Yes? And right, that makes sense. Because exactly, right, that tells us why we wait or how long we can wait, right? We can wait, of course, right? Of course, here, right? Here's the extreme. What's the extreme? R equal to 0, right? Like right now, I hope, or I don't know what interest rates right now anymore. If R is equal to 0 and L star is 0, right? Which makes sense actually, which is kind of weird, but it makes sense. Why? Because, right, I mean, you have all eternity to wait, right? T equals infinity. And so, you can wait for the maximum payoff because there's no punishment, right? There's no time value of money. So, if R is equal to 0, right, tomorrow is worth the same as today to you or something like that, right? So, right, you can wait for the maximum payoff. Okay. So therefore, right, when T equals to infinity, right, the only factor that can influence your wait time is, well, several factors, right? But one of them, one of the big players is the interest rate. Okay. So the more you get punished, right, the more like the less the future is worth to you, right? Because our increase means the future is worth less to you, right? Compared to today, then the less you can afford to wait. Yes, again, makes sense. Any question about this? Three, right? If sigma increase, then right, this is clear. And again, does this make sense? Yes, right? Why? Because here, right, you can think of sigma as kind of it's not the speed, right? But in some way, right? Because sigma, right? Remember, is the variance, right? Is the volatility. The bigger the sigma, right? The wider the swing can be. Yes. The R, right, is the movement on average, right? But sigma is how wide you can swing during a average period, right? Sigma just feed on the R, right? So basically you swing something like R plus minus sigma, something like this in a period, right? Whatever. So, right, the more sigma goes up, the faster you can reach a certain level compared to the other smaller sigma, right? So for that reason, you can afford to be more greedy because you get punished less, right? By the time you have to wait, because you will wait less. Does that make sense? So all this, right, seems to be okay. And that tells us. Right? So again, right, I'm doing this because it's quite illuminating, right, to analyze. But the moral, what I'm trying to show you here is try whatever solution you come up with, right? Whatever situation, try to do some reality check, right? Match it with what you have intuition about the problem and see if it says what it says. Okay. Any question? All right. So with this, I think we are done with the American option. But I just want to say, a few kind of, sort of thoughts about this, right? So some questions just for fun, because I think American option is really a very interesting topic to think about. The first thing is maybe, again, right, for obvious reason, we don't do this, but why? What if we think about it? What will happen? What if we have perpetual call? Then what?
Then our
Okay.
potential.
Yeah, go ahead. Go ahead, Kareem. I just saw what you made. Go ahead. What do you say?
Wait, I was gonna say the potential max that like max profit is like infinite, so you would never exercise and just hold on forever.
Right. So what Jingmei said and what you said, right? I would agree. But does that mean we don't have a price, or is there a price? What you say, I agree with, right? But let's not settle with an easy answer, right? Okay, correct. So what are we implying about pricing? No price? Infinite price? Does that mean I should charge an infinite amount of money for a perpetual call?
I think any price would be like you should theoretically take it.
I think even at the intuitive level, there's a lot of trouble with that, right? Because you charge any price, that means, no price, another extreme, right? But Kareem, right? One very easy thought exercise will show that what you say is problematic. Because clearly, right? Suppose I have two perpetual call. Let's say same stock, but with different strikes. then clearly the one with lower strike would be more worth, right? Agree?
Yeah.
So that means there's some comparison. That means that you cannot just charge whatever price. I think. I don't know. Maybe I'm wrong. Maybe I'm wrong. All right. I don't know. But no price, right, Jingmei, again, right? My argument, right, would, maybe, right? So you just try to change the parameters. You would feel intuitively that things depend on something. All right. So again, right, don't just take some easy thing as given, right? Think about it. So here's my solution. And I think, right, check me on this. My solution is this, right? Of course, I agree with this, right? But the question is price. The solution is, well, why don't we consider a regular call and then push t to infinity, right? By regular call, I mean regular European call. Then shouldn't it, oh, by the way, right, this sounds like a very good interview question, no? Right? Then shouldn't this be, at least give me some idea about what the price is? So a regular call, right? What's the price? A regular call, the price is? Yes. So if I push t to infinity, what happens to this object? What happens to this object? Well, assuming r is positive, right? If r is positive, then clearly the second term goes to zero, right? Because I don't care what this guy is bounded by one, this goes to zero, right? What about this? Well, now you see, right, in the plus part, right, this goes to infinity, right? Because the square of t cancel, right? So this will go to 1. So the price goes to does that make sense? I mean, my solution makes sense. Does it make sense financially? All right, think about that. It seems okay, I think. But, I just thought about this recently, so I didn't really draw too much into it. So what it suggests is, right, if you trust my solution, I don't find my solution problematic mathematically. I'm not 100% clear on the intuition yet. But what it's saying is, right, that for perpetual call, it's like holding a stock. Seems okay, but you think about it, all right? But I think my solution is correct. But any question about this? But right, my point though is that you should not, right, just settle with easy question, right? Easy solution. You should think about it a little bit. All right. So the next question, right, is about what about the t finite? Meaning, right, of course, like, so whenever you have a successful procedure, right, this seems very successful, right? You should try to apply it to other situations. Not that you expect it to be successfully applied, but you should see why it doesn't apply, where it fails. So you learn. All right. For example, right? I mean, here I was just purely doing a Black-Scholes approach. But what about doing the above approach for potential call? Can you, right? Can you argue out a solution? Basically, I propose that my solution is X when I try the above. Can you, right? But I'll leave that for you to play around if you want. Here, right, is about what about the PDE itself, right? Meaning minus RV plus V sub t, right, plus V sub x Rx, so plus 1/2 V sub xx sigma square x squared is negative, right? And equal to 0. So, right, what if I introduce the t dimension on it, right? What happens? What's so hard about this? So first of all, right, notice that, hey, I can still draw a picture, right? I can still draw a picture in X. And let's take the put option, right? Just to make it easy. If I draw a picture in X, right, then this is still a put option, right? I still think, right, there should be a part where the value, right, is above. And clearly, right, so, right, let's take phi of X to be the put option. Clearly, right, I mean, this should be the continuation area, right? Because the payoff is 0, so I should continue, right? So something like this, and then something like this. What do I know? It looks exactly like the above. So why the complaint, right? Maybe, I'm just pretending that it's difficult. It's not. It's easy. Same solution, right? The same picture applies. I can solve for a problem. What's wrong? All right, let me save you the suspense. What's wrong is the last thing I didn't draw purposefully on the picture is this L star, right? Anything about this L star that we should note?
It's dependent on t.
Correct. Now, L star is a function of, technically speaking, time to exploration, t minus t. But yeah. All right. And therefore, right, basically, this is a picture at some time, little t. Then you have something like this. But this guy will move as soon as t move. So it's not the same static picture as we had above, right? So we actually have no idea what this L star look like. All right. We have no idea what this L star looks like. And that exactly is where the difficulty is. Okay, we don't know how the L star looks like. Okay, so we cannot solve for this because, right, L star is no longer a constant. Okay, just a small change like this will change the whole thing. All right, so I just want to mention that. All right, any question? All right, so we're done with the American option. The last part, the last thing we want to discuss, we will discuss in this course is change in numeraire. All right, And I want to sell this as FX modeling, foreign exchange. All right. But again, we don't have a chance to go into this in this class. I'll probably say a few words at the end. This technique actually is more general than just foreign exchange modeling. It's easiest to tell you what it is under this financial context. But this is a more general technique that can have applications in, bond pricing and that kind of thing too, right? Again, which we don't have time to go into this course. All right. So under the umbrella, right, of FX modeling, what do we want to have in mind? So we'll start this right next Monday, but I'll just want to tell you the setup real quick. The setup now is, right, usually we have the stock, right? And usually we just go straight to a Black-Scholes model like this, right? RSTDT, sigma ST, this, right? Now we can't, because actually so basically we usually look at one asset, right, market. I told you, right, at some point that you can do more than one asset, but we never did it really seriously because there's no need to. But now we need to. The reason is this, that the market we naturally want to consider will have a stock for sure. And we will go back to the physical model for a good reason. I'll explain. I might have another name for it, but let's just do it now, right? Called sigma 1. The reason is, right, besides the usual stock, right, Google stock, Apple stock, whatever you want, we have another one called the foreign exchange rate. All right. So Q is foreign exchange rate, right, at time t. So in case, right, of course, I think everyone knows what foreign exchange rate is about. But one thing that can be very confusing is, going from where to where, right? Is it going from euro to dollar or dollar to euro, right? So the direction of unit will be important, right? Unit will be important to not be confused, all right? So the clue is you can kind of look at what context we're looking at here. So basically, sorry, so ignore this, right, from here. So what we have here is something we call a domestic market model. And, we're a little bit biased here, we're in the US, so you can think of domestic as US. So what this means, right, is you think of this as some price process. What price can it be if it's a foreign exchange? So you can think of it as, right, the price of a 1 euro, for example, in dollar, right? So it's dollar per euro, right, as a unit if you want, right? QT, right, or price of 1 euro in dollar, right? Or if you like Chinese yuan, you can say price of 1 yuan in dollar, right? But that's what it is. Now, to make matter even more interesting, these guys don't have to be the same ground motion. Why? Because this is the noise, right? The fluctuation of Apple stock. This is fluctuation of the euro or the yuan, whatever, right? Why you think they must be the same source of noise? So we could have different sources of noise that somehow are correlated in some way, right? The price of euro go up might influence the movement of Apple stock, but not in a very direct way, whatever, right? The point is though that why do we have to backtrack now to the and actually, right, we will need to have more often than not, we need to have two sources of prime motions because we have two assets now. Remember, right, the existence of the risk neutral probability, right? So actually, we will need two prime motions, remember, from the lesson in the past. And so that's the one thing, right? So we cannot jump to here right away. More importantly, right, we will call this domestic. Why? Because there will be a phenomenon like this that we'll look at in later section. So this is like Apple stock listed in the US market. So it will be under the dollar, right? But Apple stock can also be listed in, I don't know, the European market or China market, where there, right, the share will be listed under euro or yuan. Yes. In other words, there could be an option for Apple or whatever you want to look at in the foreign market and have a call option on that. So we do KF here because this is a strike but quoted in the foreign unit of money, like euro or yuan, right? How do we price this? We must price it by foreign risk neutral probability. All right. Of course, there's another interesting thing to do here. We can translate this into the domestic market, right, by exchange rate, and then price it under the domestic market and translate back, etc. So the point is, these two ways of approaching things must be consistent, and what does this guy mean, etc. How do we find it, right? And that's what change in numeraire is about, right? We are changing the numeraire. By the numeraire here, we'll talk about basically is the domestic money market versus the foreign money market, right? Which doesn't show up here yet. All right, so we'll talk about that. So that's the topic that we will hopefully cover during the last week of the course, and then we'll be done. Okay, so that's that. All right, so I'll see you next Monday.
Thank you, Professor.
Yep, thanks. Yeah, thanks.
Can I ask a question?
Yeah.
Yeah. Could you explain again why the interest rate increase, the L star will increase too from finance perspective?
Oh, yes. Very simple, right? Interest rate is the cost of waiting, right? It punishes you for waiting too long because, again, right, from your perspective now, right, you're evaluating the payoff you'll get in the future. Yes, I mean, very simple, right? Suppose interest rate is super high now, and I promise you I'll pay you $1,000 in 10 years, versus I promise you I'll pay you $1,000 right now or in 1 year. That makes a big difference, right? If interest rate is very high.
Yeah.
Right. So L star, right? Because your payoff, your maximum payoff is K minus L star. Right. And because the stock moves whenever it moves, right? So basically you try to maximize your payoff by waiting for the stock to go as low as it can, right? Which is L star. But the longer you wait, right, the less that payment will be worth to you if R is very high. Does that make sense? So
Yeah.
if R is high, then basically you cannot afford to wait too long, because even if you get a large payoff, that means nothing when you translate back to the current.
Yeah, that makes sense.
Mm-hmm. Okay.
Yeah, thank you, Professor.
Sure.